So now let's move to the next period, period 2, a row below what we've just done with hydrogen and helium. So just like before, the number of molecular orbitals that are formed is equal to the number of atomic orbitals that we start with. They combine effectively with other atomic orbitals that have a similar energy level. And then how well they combine is related to their overlap, how much overlap there is. And they're still going to follow Hund's rule, which means we're going to go all spin up and then all spin down, and Pauli exclusion principle, meaning we can't have like two spin up in an orbital. So let's look at lithium 2 or Li2 and see if that exists. So lithium's electron configuration is 1s2, 2s1. It has 3 electrons. And so if we have 2 lithiums, let's draw one lithium. We have our energy diagram here. We have the first lithium has 1s for this lithium, and then it has a 2s up here. The other lithium is going to have similar energy, 1s and 2s. Okay, and so then for this first 1s, this 1s set here, we're going to have a bonding, a sigma and a sigma star for that, and they're a similar energy, so these are the combination we're going to get. And then for this 2s, we're also going to have a anti-bonding and a bonding level. Oops. Okay, so let's fill it in. We have 1s2, 2s1, 1s2, 2s1. So we have 4 electrons down here and 2 electrons up here. And so we'll fill in the bottom first, lowest energy first. 1, 2, 3, 4, and then 2 above, 1, 2. So notice up here, these guys cancel out. We have a bonding and an anti-bonding, meaning bond order of 0. And up here, on the higher one with the 2s orbital, we have our bond order will be a half times 2 in the bonding minus 0 in the anti-bonding, so a bond order of 1. So lithium 2 does exist, yes, and it has a bond order, a single bond. So notice that down here in these core electrons, the core electrons for the atoms are going to cancel out. We're going to have both bonding and anti-bonding here, so they don't really play a big role in the bonding. Just like before, valence electrons are going to do most of the work, and so we don't have to worry about writing any core electrons moving forward. We could just stick with valence. If we were to do the full electron configuration though for this molecule, we would do sigma 1s with 2 electrons from down here, sigma 1s star for the anti-bonding orbital, also with 2, and then we have a sigma orbital for the 2s that also has 2 electrons in it. Okay, let's practice doing the helium-2 cation. So in this case, we have 2 helium atoms. We have, well, this first helium atom has 2 electrons, right? We have a 1s, and it's filled up. This other helium also has 2 electrons, but since the molecule only is a cation, we're only going to write 1 in this 1s here. So then, let me actually move this down so we can have more room. All right, so we now have the bonding or sigma orbital down here, anti-bond up here, and we'll fill it in. We have 3 electrons, so we'll go 1, 2, 3. So our bond order is going to be a half times 2 minus 1. So bond order of a half. So the lower the bond order or the smaller the number means the weaker the bond. Having a minimum of 0 meaning no bond forms or the molecule doesn't exist. So this does exist based on this theory, but it is a weaker bond. So doing the electron configuration for helium-2 ion, we would do that sigma 1s has 2 electrons in it from right here. And then sigma 1s star has 1 electron in it. So
2, and 1.
Okay, so let's get some p orbitals involved. If we continue going down on the second period, we can see that we have some 2p orbitals. And just like the s orbitals, p orbitals also undergo overlap, and we saw that with valence theory, right? P orbitals can either have direct overlap, like these z ones, where they are gonna completely bond, or have a node, an antibond. But they could also have a sideways or next to each other overlap, just like we had with our unhybridized p orbitals before. So our sideways overlap, we see if we have these two px orbitals next to each other, they're going to do the little like sideways overlap like that. And the opposite of that looks like a node like that, where you have almost like butterfly wings. And then similarly, the y orbital does something similar, where we get a pi bond, but it's flat, and butterfly wings also flat. Just like s orbitals, we have bonding and antibonding. We get sigma and sigma star from the s and the p atomic orbitals, and we get pi and antibonding, pi and pi antibonding from the other 2p orbitals. So we get 2 pi bonds coming from the sideways overlap, and 1 sigma bond coming from end-to-end overlap from the p orbitals. Just like we mentioned before, direct overlap is the stronger one, right? It's just more connection, making it harder to break. Because it's stronger, that means it has a lower energy for the bond. And so we'll see the raising and lower energy is greater for these, meaning you'll see the sigma one. So here's our p orbitals. We'll see the sigma orbital that gets formed, and the anti-sigma be the kind of like the bookends, one at the very bottom, one at the very top. So because they are the most stabilizing or destabilizing in the case of antibonding. So we'll often see arrangements where we have a sigma, 2 pi, 2 anti-pi, 1 anti-sigma. In some cases, though, there are the case where the s orbitals can interact with that pz orbital that forms the sigma bond, right? These both form sigmas, more than they do that with the pi forming p orbitals. And so this is actually going to raise the energy of the pz orbital, meaning the pz orbital here will go above the pi bonding ones, and it actually lowers the energy of the s orbital. So kind of like they separate from each other. And so what we get is a bigger separation here. It doesn't really change a whole lot as how you draw it, but you'll see the sigma bond from that p orbital go above. This happens with boron, carbon, and nitrogen. So the earlier ones, so molecules 5, 6, and 7. And then with oxygen, fluorine, and neon, they have this normal arrangement. So you kind of do have to keep track. Initially it goes 1, 1, 2, 1, and later on it goes 1, 1, 1, 2. So here are those examples. We can see where we have that interaction. We split here. We have boron and carbon and nitrogen all having the pi orbitals before the sigma orbitals, and then later on with small interaction we have the pi interaction above the sigma, which is kind of like what we would normally expect. We can also calculate bond order, so we would do the sigma first, so from here, and then we would do above. So we would still always do the non-bonding, or the bonding minus the anti-bonding for all of them. So here I have 2 bonding plus these 2 bonding, so I have 4 minus these 2 anti-bonding, so it gives us a bond order of 1. It also helps to describe how magnetic something is. So if we have unpaired electrons, that's going to lead to magnetism. So unpaired electrons leads to something being magnetic, or we call that paramagnetic. When we have everything is paired up, all of them are paired electrons, that is called diamagnetic. So we can see here boron is paramagnetic, carbon gets all paired up, so it's diamagnetic, so does nitrogen. Here we see oxygen with some unpaired electrons here in the antibonding orbital, making it paramagnetic. Fluorine is diamagnetic. Now we can see here with neon, a noble gas, all of the orbitals are filled up, meaning that the bonding are going to cancel out the antibonding and we'll have a bond order of 0. So neon, this diatomic molecule, does not exist based on this theory. So this one is exactly what I just said. Diamagnetic means that we actually don't have an attraction to a magnetic field. There's actually a slight repulsion to a magnetic field, so we just say, it's not magnetic. Paramagnetic means that they're in the presence of an a magnetic field, that there will be an attraction. So oxygen, if we look back at the diagram, we saw that there were some unpaired electrons, and you see that. So when we pour liquid nitrogen, if we look at this picture down here, we pour liquid nitrogen by a magnet. Let's see if I can zoom in. It actually does attract to the magnet. So this is just an interaction that, and they actually adjusted the molecular orbital diagram to account for this interaction. Lewis structures, Vesper, and even valence bond theory on their own does not predict it, but this MO diagram does. And then both of them do. Lewis and as well as MO do agree that it is a bond order of 2, meaning it's a double bond. And so there is some ways that there is overlap. And like I said earlier, these theories really do build on each other and they kind of back each other up the more complex you get with it. So it's a nice way that MO theory does support some of the things we saw earlier with Lewis theory, but it just adds additional information. Okay, so let's practice and see if we can predict whether this dioxygenyl ion, O2 plus, and acetylide ion, C2 2 minus, we need to predict their magnetic properties and their bond orders. So first, let's start with O2 plus. So for O2, the electron configuration for the valence electrons is 2s2, 2p4. So there are 6 valence electrons there. So we're going to draw one oxygen atom here and one here. We're going to start with the 2s on this one and the 2s on this one. And then we'll have the 2p here and the 2p here. So oxygen, if we remember, is one of those that has low ps interaction. So the s orbitals will still have the sigma and anti-sigma bonds. And then this p will have 1 here, 2 here, 2 here, 1 here. So being sigma, pi, anti-pi, anti-sigma. So then we'll have it looks like boop, boop. Okay, and we'll fill them up. So we have 2 in the 2s, and then we have 4 in the 2p. I'm going to do 1, 2, 3, 4 here, and I'm only going to do 3 here because it is a cation. So 1, 2, 3. We need to remove an electron somewhere. All right, so we're going to fill up 1, 2, 3, 4 from our 4 electrons down here. And then here we have a total of 7 electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7. Notice I filled up those degenerate orbitals right here. I filled them up like we would the p orbitals here, right? Up, up, down, down. So we can see there is one unpaired electron, so we would call this paramagnetic because there does exist one. And when we find the bond order, we're going to do a half times the number of total bonding electrons. So we have 2 here, another 2 here, another 4 here. So we have a total of 8 bonding electrons. And then our non-bonding electrons are going to be 2, 3. So 8 minus 3, equals 5 halves, or 2.5. All right, so now we're going to move on to the acetylide ion. Let's do this one in green. So for C2, we have 2 extra electrons. Keep that in mind. So we're going to do, for carbon, its electron configuration is 2s2, 2p2. So again, we'll have 1 carbon here, 1 carbon here. We'll have the 2s, and the 2s, and the 2p, and the 2p. 1, 2, 3, 1, 2, 3, 1, 1. All right, and we'll fill it in. 1, 2, 1, 2, and then we also have plus 2 electrons in here. So we're gonna do, I'll do 1, 2, 3 on this one, and 1, 2, 3 on this one. You could do them both on the same. It doesn't really matter, because when we bring it all together, they'll all go into those molecular orbitals. All right, so we're gonna do our s orbitals. We're gonna form those sigma bonds, so sigma and anti-sigma. And then our p orbitals. Now remember, carbon does have a large sp interaction. So what's gonna happen is we're gonna have the 2p orbital, or 2 pi orbitals first, then a sigma, then 2 anti-bonding, and then a sigma. All right, so I'll label those pi, sigma, anti-pi, anti-sigma. So we'll fill her in now. We'll go 1, 2, 3, 4 for this layer. And then here we have 6 electrons total, so we're going to go 1, 2, 3, 4, 5, 6. So they're all paired up, so we will call this diamagnetic. And they the bond order is going to be a half times, we have bond 2, 4, 6, 8, minus these 2 here, so minus 2. So we have 6 divided by 2 is a bond order of 3. So a triple bond would be what we see for acetylide. Let's do the electron configuration for our acetylide ion, C2 over here. So we have our, starting with our valence orbitals, we have sigma 2s with 2 electrons in it, sigma 2s star up here with 2 electrons in it, and then we go up to our pi orbital here. Now our pi for our 2p have 4 electrons in it, and then we have our sigma for our 2p, and it has 2 electrons in it. So that is how we would write those electron configurations.